1.
Oh my God, it worked. Okay. Thank you, Sam, for the introduction, and thank you all for coming. As Sam said, I'm going to be telling you about differentiating matrix functions. And just to give you a slight heads up about what is to come, if you have a scalar function, f, the matrix function associated with it is the function that takes an n by n matrix. It'll be a Hermitian matrix for us, but just think n by n matrix, and it assigns f of that matrix, which will again be an n by n matrix. And I'm going to write f tilde for this function. I'm going to explain what all of this means, but just so you have an idea, this is the function we're going to be differentiating. It's going to be a function from some n by n matrices to some more n by n matrices. So as such, I have to first tell you about what f of a means. That's a construction known as functional calculus. Most of you have seen it in various capacities. Probably all of you have seen it at least when f is a polynomial and when f is e to the x. Those are common functions to apply to matrices. But I'll tell you a little bit systematically what I mean. And then I will tell you about what differentiation is for me, maps between norm vector spaces. And then I'll get to the meat of the talk, which is the actual act of differentiating this function. Now, this is going to be, feel free to interrupt me at any point if you have questions. It'll be a little bit informal, I guess. Okay, with that, let's get started. So as I mentioned, I'm going to divide the talk into 4 sections. First is I'm going to tell you what functional calculus is, what it means to apply f to a matrix. Second, I'm going to talk to you about differentiation of maps between norm vector spaces. Then I'm going to tell you about the main result and formula, which involves the derivatives of f tilde, the matrix function. And then I'm going to tell you a few words about operator functions and derivatives of operator functions, which is the infinite dimensional version of this construction. And that's still a pretty active area of research, and it's highly technical, so I'm really just going to do big picture stuff. All right, without further ado, let's do this. First, we'll talk about functional calculus, or if you will, funky calc. Now, I'm going to stick to diagonalizable matrices for various reasons. I'm going to be concerned with Hermitian matrices, which are all diagonalizable. And I'm going to have a particular view of diagonalization that I'll tell you about in a little bit that's going to be useful for the formulas. So you can do functional calculus more generally, but I don't care. I'm going to tell you, I'm going to keep it as elementary as possible, and I'm going to do diagonalizable matrices. So let's set some notation. Let n be a natural number, and MNC be the set of n by n complex matrices. And I'm going to recall that A is diagonalizable if there are other matrices B and D, such that B is invertible, D is diagonal, and the diagonal entries, lambda 1 through lambda n, are going to be the eigenvalues of A with multiplicity, such that A is B, D, B inverse. And remember, the columns of B are the eigenvectors of A, or a basis of Cn of eigenvectors of A. Now I'll set some notation. We're going to have sigma of A. I'll call that the spectrum of A, and it's going to be the set of eigenvalues of A. Remember, these are complex numbers. Then I'm going to set affix an arbitrary function of the eigenvalues. So a complex valued function of the eigenvalues. And I'm going to define f of A via the diagonalization I chose above of A as B f of the diagonal matrix, which means you just make diagonal matrix with f of the diagonal entries, and then B inverse. This, on the face of it, seems to depend on the diagonalization, but a nice exercise / lemma will tell you that the above definition of f of A does not depend on diagonalization of A, that I chose the B inverse. Now, I told you I'm going to stick to diagonal matrices or diagonalizable matrices, but I'll make a remark here for those who know a little bit more functional analysis. The usual and correct starting point for functional calculus is holomorphic functional calculus, which it doesn't matter if you understand the words I'm about to say. This works generally for Banach algebras. And if you use holomorphic functional calculus, I could give an alternate version of this talk with equally fruitful motivation. perhaps even more convincing motivation, but it's much less elementary. So I'm going to stick to as elementary as possible. All right. The examples that I mentioned at the beginning of the talk are going to be the ones you're most familiar with. So first, if you take polynomials of a matrix. So as I've defined it, if f is a restriction to sigma of a, the spectrum of a, of the polynomial with coefficients cj, then as you can check from the definition, f of a is the thing that you think it should be, which is the same polynomial of the matrix A. The second example is the exponential function. If f is the restriction to the spectrum of A of z maps to e to the z, then once again, one can check that f of a is actually the power series expansion that we usually use to define e to the a. Those are nice exercises to check, and they turn out exactly as you might hope, and therefore help to justify the notation f of a. So now I alluded before that I'm going to tell you about a different view of diagonalization, and one reason this is going to be equivalent to diagonalization basically, but it is better in my opinion because it takes away the inherent non-uniqueness in diagonalization. So you have a few choices you can make when you diagonalize. Number one, you can reorder the eigenvalues in the matrix D, the diagonal matrix. And then number two, you can reorder the columns appropriately, but you can also pick different bases of the eigenspace. So what the lemma I'm about to quote for you is an alternative characterization that is sort of basis free of diagonalization of a matrix. So an n by n matrix is diagonalizable if and only if it admits a what you could call a spectral resolution. So it's a decomposition into a sum over its eigenvalues of lambda p lambda, where this set p lambda is some n by n matrices that are called a resolution of the identity. And what does that mean? It means first that they sum up to the identity matrix, In, and that second, when you have distinct lambda and mu, p lambda p mu is 0, and when you have the same lambda and mu, you get p lambda squared is p lambda. What that says is that p lambda is a projection matrix, and that the images of p lambda and p mu are linearly independent. And then this says that their images span Cn. So in some way, choosing a projection, a resolution of the identity is the same as decomposing Cn into a direct sum of certain subspaces. And actually, you can use that statement that I just said and the fact, this identity to show that this decomposition, in the case that you have a diagonalizable matrix, is unique. And that's basically because you can show from this identity that these have to be projections onto the eigenspaces. They don't have to be the orthogonal projections, we'll get there, but they are projections determined by how A has its eigenspaces split. So this is the kind of invariant view of diagonalization that I'm going to prefer, and that's going to be useful for us in formulas. This also gives a nice expression for f of A. So if you have this diagonalization or this resolution of A, f of A is going to be the resolution sum over the eigenvalues of A, f of lambda p lambda. So for various reasons that I'll get to on the next slide, we're going to care mostly about unitary diagonalization and unitarily diagonalizable matrices. So let's remember what that means. A is unitarily diagonalizable if you can diagonalize it with a unitary B. And a unitary is just a matrix so that B star is B inverse, where B star is the conjugate transpose of the matrix B, which is called the adjoint. So B adjoint equals B inverse. That's what it means to be unitary. And in this case, that resolution from the last slide that I just told you about is such that the P lambda is Hermitian, meaning it's self-adjoint, meaning its adjoint is itself. This actually implies that P lambda is the orthogonal projection onto the lambda eigenspace of A. So in the case that your matrix is unitarily diagonalizable, that decomposition from the last slide is quite nice. It's a decomposition where you have lambda and the orthogonal projection onto the lambda eigenspace. And actually, this special situation, the unitary diagonalizable situation, is characterized by the spectral theorem, with parts of which are very frequently covered in basic linear algebra classes, but it's not always the case that the full spectral theorem is covered. And from a linear algebra perspective, I would call this a full enough spectral theorem. A matrix A is normal, i.e. it commutes with its adjoint, if and only if it is unitarily diagonalizable. So that's the full situation. This commuting with your adjoint gives you the full situation. To recap, that means that if A is normal, I guess if and only if A is normal, then there's a unique resolution of the identity that is self-adjoint or Hermitian, such that A is decomposable in this way, sum over the spectrum of lambda p lambda. And I'm going to label for a normal matrix A, I'm going to label p lambda A as this particular resolution of the identity. It's canonical diagonalization, if you will. And I'm going to call it the spectral resolution of A. All right, so the reason we care about unitary diagonalization is going to be a proposition that I'm going to put on this slide, and it has to do with an expression for the operator norm of a normal, i.e. unitarily diagonalizable matrix. And I'm going to recall what the operator norm is. Remember, if you have V and W normed vector spaces, so these are vector spaces with a notion of length, and if you have a linear map from V to W, then its operator norm, which I'm going to denote norm sub V to W, is the supremum of the W norm of TV, where V is a vector with norm at most 1. And this can be infinity sometimes, like if V is infinite dimensional, but often we're going to restrict to the bounded case, which is when this is finite, and it's called the operator norm of T. Here's the main reason we want unitary diagonalizability. If you have a normal matrix, i.e. a unitarily diagonalizable matrix, then the operator norm of the matrix is just the biggest absolute value of whatever eigenvalues the matrix has. And I will continue this convention of shortening the operator norm of a matrix, which is a map from Cn to Cn, as just this norm sign. Okay, so as a consequence, you can show that if A is normal and F is a function, then F of A is normal. And so the proposition then gives that the operator norm of the matrix F of A is actually just the maximum value of the function F, of the absolute value of the function F over the spectrum of A. That'll be useful for us later. So now that I've given you basically all information that I want about functional calculus, that's all the elementary information about functional calculus I wanted, I'll introduce the matrix function, which is going to be the thing we're going to differentiate, and then I'll talk about differentiation. Okay, so I'm going to introduce this notation for the set of Hermitian matrices. Those are the ones whose adjoint is still themselves, and this is denoted MNC sub SA. SA is for self-adjoint. First of all, the Hermitian matrices form a real subspace of MNC, and all members of the Hermitian matrices have real eigenvalues. So I'm going to consider functions that have domain the real numbers and codomain the complex numbers. That's the reason. It's because we're considering just Hermitian matrices. Now we're going to fix the following notation. So fix an n and a function from R to C, and we're going to write f tilde, as I said at the beginning, as the function from Hermitian matrices to n by n matrices that is defined as A maps to f of A, which is just f restricted to the spectrum of A applied to A via functional calculus. And this map I'm going to call the matrix function associated to A. As my advisor's advisor told them, and as they now tell me, if you have a function, then you should differentiate it. And that's what we're going to do. Before I start talking about differentiation, though, I'm going to remark, I told you guys that normal matrices are the ones you can consider if you want to talk about unitary diagonalization. And so you might ask, why would I restrict to Hermitian matrices and not just go with normal matrices? The answer is that I want to do calculus. And if you want to do calculus, you should have like a vector space, or at the very least a submanifold or a manifold to do calculus on. Now, the set of normal matrices is not a vector subspace. but actually even worse, it's not even a submanifold. So it's probably not the right thing to do calculus on. That's why we're going to restrict to the Hermitian matrices. So that was just a nice side comment for the geometrically minded. Okay, let's talk about differentiation of maps between norm vector spaces. There are two common notions of differentiability: Gateaux, which is a kind of weak version, and Fréchet, which is a stronger version of differentiability. Gateaux is more intuitive. Fréchet is the thing we're going to be concerned with, but I'll introduce both of them just so that you can know that the quantities we're considering are really just different directional derivatives. So let's let V and W be norm vector spaces over either R or C, or if you want any norm field, that's for Alex. We're going to let V W to be the linear maps V to W with operator norm finite. So these are the bounded linear maps. A map F from V to W is called Gateaux differentiable at P if all the directional derivatives exist. So this quantity right here, partial HF at P, is the directional derivative of F at P in the direction H. And it's defined to be this derivative, which is the limit of this difference quotient. This is you often see this in calculus when V is Rn and W is Rm. And we're going to call F Fréchet differentiable at P if there is a linear map, a bounded linear map, DFP, which I will call the Fréchet derivative or the total derivative or just the derivative, such that f of P plus H minus f of P minus DFP at H is little o of H, the norm of H. More precisely, it means that this limit is 0. And what this is saying is that near P, F is order 1 approximable by a linear map. That's basically what differentiability at P means. And that second definition is perhaps a little less intuitive, but when you are Fréchet differentiable, you're Gateaux differentiable, and this linear map applied to H is really just directional derivative in the direction H. So that's what you should think of when I write big DFP at H. You should think the directional derivative in the direction of H. All right. The most important example for us is going to be the power map. And for that, I'm going to need a normed algebra. And if you're wondering what a normed algebra is, it is a unital algebra over the complex numbers, B, with a norm that satisfies norm of AB is less than or equal to the norm of A times norm of B, and the norm of 1 is 1. So that's what a normed algebra is. The most important example to keep in mind is going to be the n by n matrices with the operator norm. That is a normed algebra. Now, if pi m from B to B is the mth power map, that is the map A maps to A to the m, then one could show that pi m is actually Fréchet differentiable, and the formula for the derivative is given as follows. So the derivative of A to the m at B is this sum, AJB, AM minus 1 minus J. Now, this may look a bit funny, but let's pretend that A and B commute. Well, if A goes on the other side here, these J's cancel out, and what you just get is the number of guys in the sum, so that's m times A to the m minus 1 times B. So remember what the derivative of t to the m is, where t is a real number, that's m to the t to the m minus 1, sorry, m times t to the m minus 1. So this is the non-commutative version of the usual power rule for derivatives that you're used to. And if you want, you can heuristically use the non-commutative product rule to suggest this formula. If you have some smooth curves, A1 through AM, and you want to take the derivative of the product, then you do the usual thing where you differentiate only one, and you leave all of them alone, and you add up the result. So this is the non-commutative product rule. And if you take the AJs to be A plus TB, then this formula is suggested by that little calculation. But the take home is just going to be this formula that we're going to go forward with. Okay, so I'm going to focus mostly on first derivatives, but I am going to state a result or two about higher derivatives. This is a bit annoying notationally, so feel free to just completely disregard this slide if you get confused or something. Of course, you can still ask me questions, but I'm just letting you know this is not super necessary. So if you have now k normed vector spaces v1 through vk and another one w, we're going to define bk v1 through vw with values in w to be the set of k-linear maps from these guys to this, with the operator norm defined in a similar way to when you just have k equals 1. And these are going to be the bounded k-linear maps from v1 through vk into w. We're going to use an identification of the bounded k-linear maps with the bounded linear maps from the first one to the bounded k-1 linear maps from v2 through vk into w. And that is actually an isometric isomorphism via the map, which does the only thing you can possibly do, which if you have somebody with k inputs and you need somebody with 1 and then k-1 inputs, you do the first one and you take the remaining k and you map to the only thing you can do. Plug in the first one that you had and plug in the rest after. We're going to use this identification to define the higher derivatives. And I told you it's a bit annoying, so don't worry if you're not absorbing it all, but bear with me. Okay, so let's say k is greater than or equal to 2, and we've already defined k-1 times Fréchet differentiability for f, and the k-1 Fréchet derivative, dk-1, from v to bk-1, vk-1, w. We're going to inductively say that f is k times Fréchet differentiable if the k-1 derivative as a map from v to this normed vector space is Fréchet differentiable, and we're going to define the kth Fréchet derivative to be, as you might expect, the Fréchet derivative of the k-1 Fréchet derivative with the identification of this guy as the k-linear maps from all the copies of v to w. This is hard to digest, but the formula you might want to keep in mind is the following. So if you have the kth derivative at p in the directions h1 through hk, then this kth directional derivative formula is the one you should think about. So it's basically the somewhat intuitive kth derivative. Again, it's a little annoying when you do higher dimensional, higher derivatives, but this is the notion that I'll be using whenever I state stuff. Okay, are there any questions up to this point? Coolio. All right, here's the main result and main formula. And the way we're going to do this, so my goal is to differentiate f tilde. And the way we're going to start is we're going to start by having f be a polynomial, and we're going to differentiate p tilde, the polynomial tilde. And that is just going to use the formula from the previous couple of slides ago. And then we're going to use an approximation procedure to get more general f. So that being said, let's take a closer look at that power map in the case that we're thinking of. So if we return to the setting at the beginning, we're going to consider the function f to be pm, which is my notation for the scalar power map. Lambda goes to lambda to the m. As we showed in the example, the first example of the talk, if you have a Hermitian matrix, then p tilde, pm tilde of A is just the nth power of the matrix, but it has this spectral resolution. So over the eigenvalues of f of, or pm of lambda, which is lambda to the m, p lambda A. So that's what we saw in the first example. And then what we saw in the differentiation example is that this power map is differentiable, and its derivative formula is this. Okay, now we're going to apply this spectral resolution formula to aj and am minus 1 minus j. That yields this. So I've replaced aj with sum over lambda of lambda j p lambda a. B stays there, and then sum over mu of mu to the m minus 1 minus j p mu a. Now I'm going to rearrange the sums and bring the scalars to the left, but I'm going to leave the matrices in the right order. That gives me this, a double sum over lambda mu in the spectrum, so sum over a pair of eigenvalues of this two-variable polynomial, which we will explore more on the next slide, and then p lambda a, b, p mu. Okay, it's going to be crucial for us to identify a natural function that gives this and is related to the power map somehow. That's the subject of this slide. So if you fix lambda and mu, any real numbers, it's an easy exercise to show. You can just do it by direct calculation, or you can use like a geometric series type identity to show that that function we were just looking at, this two-variable polynomial, is expressible as lambda to the m minus mu to the m over lambda minus mu, which, again, putting the function notation in, is pm of lambda minus pm of mu over lambda minus mu. This is somewhat of a discrete derivative. You could say a difference quotient. Lambda is not equal to mu here, and if lambda is equal to mu, well, what do you get? You just, the j's go away here, and you once again just get m times lambda to the m minus 1, which happens to be pm prime of lambda, which, if you just formally put in lambda equals mu, is what you should get with this discrete derivative. So this prompts us to define, for a C1 function, f bracket 1 lambda mu as this difference quotient when you have distinct lambda and mu, and f prime of lambda if lambda equals mu. You can use the fundamental theorem of calculus to show that you don't have to do cases here. This has an expression as a nice integral from 0 to 1, f prime t lambda plus 1 minus t mu. This actually also makes it clear that if f is C1, then f bracket 1 is C2 as a function of two variables. Is continuous as a function of two variables. We're going to call f bracket 1 the first divided difference of f. So think of it as a discrete derivative, if you like, as well, or a non-commutative derivative. That's another term that floats around the literature. The previous slide, where we computed or we rewrote the derivative of the power map, by linearity, it tells you that if p is any polynomial, then p tilde, which is really just the polynomial map for matrices, is differentiable and has the following formula for the derivative. So derivative of p tilde at a in the direction of b is the sum over lambda mu eigenvalues of the first divided difference of p, lambda mu, p lambda a, b, p mu a. Okay, this is going to be the formula that we're going to aim to prove for f in C1. So here it is. The goal of the rest of this section is just to talk through a sketch of the proof of this. This is a theorem of Daletsky and Krein from 1956, and I'll talk a little bit more about that paper in a sec. If f is in C1, so it's a continuously differentiable function from R to C, then f tilde, the matrix function, is Fréchet differentiable. It's actually continuously Fréchet differentiable, but we'll just ignore that. And the formula for the derivative is what it should be. So it's this double sum of the first divided difference and p lambda a, b, p mu a. Now, this paper from 1956 that contains this result jump-started the study of double/multiple operator integrals. That's DOI or MOI. And we'll discuss that later. That has more to do with the infinite dimensional case. This paper was the first place that the infinite dimensional case arose, and also that this calculation arose. But the reason this is called an integral, I will make a little bit clearer later, but don't worry about it right now. I'll just use these abbreviations for an object such as this for now. The theorem we're going to prove, as I suggested, by approximation of f in the C1 topology by polynomials, as I will show you. So I told you we need to consider an object such as the one in this formula right here. So such an object is called a finite-dimensional double operator integral, and it's defined as follows. So take two Hermitian matrices and a function of two variables, one eigenvalue is A1, the other eigenvalue is A2. And we're going to define I super A1, A2 of G at B, where B is an n by n matrix, to be the same type of double sum. You take lambda eigenvalue of A1, mu eigenvalue of A2, G lambda mu, P lambda A1, B, P mu A2. In the last example, in the last formula, A1 was equal to A2, and G was equal to the first divided difference of F. So, I should also mention that the common notation for this in the literature is T, A1, A2, G, but I hate that because I want G to be more prominent. But this is just my notation, so you won't find it anywhere if you look. This is the standard notation. All right. So because this is manifestly linear in the B argument, this is a linear map from matrices to matrices. And we're going to do a little operator norm calculation on this. So here's just the expression defining I, A1, A2, G of B. I'll use the triangle inequality to bring the norms in. G lambda mu pops out with an absolute value. Then I use the normed algebra property to break these guys up. But these are non-zero projection matrices, which have operator norm 1, and norm of B just sits there. Now, that gives us, first, we can pull out maximum value of the function G. We can pull out the norm of B, and then these are both 1. And remember that A1 and A2 have at most n eigenvalues. So this sum has at most, n squared guys. So that's where this n squared comes from. So reading this as an operator norm estimate for a linear map from matrices to matrices, we get that it's, I'm going to do norm with 3 bars for this. It's operator norm as a map from matrices to matrices is less than or equal to n squared times the maximum value of the function on spectrum of A1 cross spectrum of A2. Now, I'm going to mention, this was a really simple calculation we did. You can go through a little bit of a more painful calculation to show that you can improve this n squared to a square root of n. That is, I wanted to mention this because that's basically the best you can do. And this is what should alert you to the fact that the infinite dimensional case is harder. This blows up as the dimension blows up. So you can't get, there's a theorem that says also that you can't get these operator norm estimates that you might need for the argument I'm about to do in the infinite dimensional.
So just out of curiosity, Vaki, can you mention like where you get the savings from, roughly speaking here?
Yeah, it's this is an operator norm estimate. Already with the operator norm estimate, you can improve it to n by first doing functional calculus in the A1 variable here. That gets rid of this, which gets rid of a whole n. But the place you really save from n to square root of n is if you compute the Hilbert-Schmidt norm of this matrix. If you just literally keep identities until you can't anymore, you get a square root of n.
Okay, cool, thanks.
Yeah, it's basically, yeah, you have to pick smart bases to do this calculation. It's a little bit of a pain, but it's the best you can do. All right, any more questions? Cool. So now I'm going to sketch the proof of this theorem. Emphasis on sketch. Ask for any clarifying things, but there's going to be one statement that I just won't give you that finishes the argument. But let's see how it works. So first, as we noted at the beginning of this section, we know this formula for polynomials. We did it for polynomials as a corollary of the example of derivatives we did in the differentiation section. Now, as a little exercise, I recommend you note to yourself that if f is C1, then I can use the classical Weierstrass approximation theorem to find a sequence of polynomials, Qj, such that Fj goes to F, Qj goes to F, and Qj prime goes to F prime uniformly on compact subsets, Sj. And the hint is first find a sequence that approximates F prime and then integrate that sequence to approximate F. Now we're going to pick our favorite compact set, the ball. We're going to let R be greater than 0 and let Kr be the operator norm ball around 0 in the Hermitian matrices. Then, if you look at Qja minus Fa, then this is really Qj minus F applied to A, which has operator norm maximum over the spectrum of Qj minus F. Now, the spectrum is of a matrix with operator norm less than or equal to R. So these numbers will be absolute value at most R. So this becomes supremum over minus r to r of qj minus f, which goes to 0 because of the uniform convergence on compact subsets. That's number one. Number two, we're going to look at the derivative of qj tilde at A and the putative derivative of f at A. That's this double operator integral thing that I claimed it was. So this is the formula I claimed, and we actually proved the formula for polynomials by citing the example of derivatives. Now, rewriting that as this guy for qj, you get sup over A of this operator norm, double operator integral involving qj minus f first divided difference. By the operator norm estimate from the last slide that I proved for you, this is bounded above by n squared, and then this guy gets the maximum value of the function inside, which is the first divided difference of qj minus f. And a little exercise that comes from the fact that you can express this divided difference as an integral of the derivative gives you that this is bounded above by just the maximum value over minus r to r of qj prime minus f prime. This again uses that A has operator norm less than or equal to r. And again, this goes to 0 as j goes to infinity. Now, these two things, if you're used to working with Fréchet derivatives, this finishes out the argument. If you're not used to Fréchet derivatives, you might think this is dubious. That's okay. You can either take my word for it, or we can discuss it more at the end of the talk if you want, but this is the kind of sketch of the proof. Are there any questions about that? Cool. So now I'm going to state the formula for higher derivatives of f tilde when f is in ck. The approach is very much similar. You prove it for polynomials, and then you approximate in the ck topology instead. Okay. Higher order derivatives of f tilde are finite dimensional multiple operator integrals instead of double operator integrals involving the kth divided difference fk of f, which is defined inductively as the function of k plus 1 variables, fk, lambda 1 through lambda k plus 1, where you do the previous one with the first k minus the previous one, take out the kth one, and go lambda 1 through lambda k minus 1, lambda k plus 1, and then divide by lambda k minus lambda k plus 1. You should think about this schematically as the discrete derivative of, the kth discrete derivative of f is equal to the first discrete derivative of the k minus first discrete derivative. Schematically, that's what this definition means. And of course, you have to modify when the lambda j are not distinct, but you'll be able to make those modifications because f is ck. I won't go through the details. There are some better expressions you can write, but whatever. Now the theorem, which really the approach comes from Daletsky and Krein in that 1956 seminal paper, but the one who wrote it down in detail, the way I'm about to state it, was Hiai, and that was in 2010. I'm not sure why people waited so long to write it properly, but for some reason they did. If f is in ck and f tilde is the matrix function, then that is k times continuously Fréchet differentiable, and the kth derivative at A in the directions b1 through bk is a symmetrization. So sk is the symmetric group on k letters of this multiple operator integral. And it's, you do the kth divided difference, and you sum over k plus 1 tuples of eigenvalues, where you plug in the k tuple here, and then you do p lambda 1a, b gamma 1, dot, 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 p lambda k a, b gamma k, p lambda k plus 1a. So this is the formula for the kth derivative. And once again, the approach is similar. It's just the formulas are slightly more unwieldy, so it's annoying to actually write down. Okay, that basically concludes the finite dimensional part of the talk. Does anyone have any questions before I hand wave about the infinite dimensional situation? Sweet. Okay, at this part of the talk, I'm going to assume considerably more functional analysis than the rest of the talk, so I'm just going to use terms. I apologize to those for whom terms don't mean anything. But just anywhere you see an integral, just think of the sum from before. That's my guidance. Okay, so first, what's the appropriate analog of unitary diagonalization in infinite dimensions? That's going to still be spectral resolution, but the spectral resolution is going to be integration against a projection valued measure instead of just summing over projection matrices. So in the infinite dimensional case, we're going to replace the matrices with bounded operators on a complex Hilbert space. H is a complex Hilbert space. B of H is bounded linear maps from H to H. And the spectral theorem 2.0 for the infinite dimensional situation says that if A is a bounded normal operator, then there exists a unique projection valued measure, PA, from the Borel subsets of the spectrum, which is called the projection valued spectral measure. This is the analog of a resolution of the identity, such that A is expressible as the integral over the spectrum of lambda against the projection valued measure of A. So once again, here's an integral, just it's a sum in your mind if you're not familiar with the infinite dimensional stuff. This leads to a definition of Borel functional calculus. And I'm going to use this notation that Bruce uses. For a measurable space omega f, we're going to write little L infinity of omega f to be the bounded measurable functions omega to c. This is the definition of functional calculus, which again straightforwardly generalizes the sum situation to an integral situation. You have a bounded measurable function. F of A is the integral over the spectrum against the projection valued spectral measure of A. All right, so that leads us to the same definition of an operator function. Fix a complex Hilbert space H and a locally bounded Borel measurable function from R to C. And we're going to write F tilde for the map that takes a bounded self-adjoint operator to F of that bounded self-adjoint operator, which is another bounded operator. We're going to call this the operator function associated to F. Important historical comment. When trying to differentiate operator functions, researchers have historically considered F of A where A is possibly unbounded. This is because they were interested in perturbation theory as their applications. That's how this whole thing came about, actually, of differentiating operator functions. This situation came up in my research in the context of free stochastic integration and matrix SDEs and free stochastic SDEs. And in that situation, you don't need unbounded operators, and you can actually mimic the finite dimensional approach in a certain precise sense. Well, maybe we'll talk about it in a second. First, I have to tell you, all right, we needed an expression like this to write down our case derivative from the matrix case. And it was a sum over a bunch of projective resolutions of the identity. And what you should do is just replace the sums with integrals naively. And if you do so, you're going to come up with an expression like this. It's an iterated integral of PA1s, and then you stick a B1 in there, and then PAK, you stick another BK, and then PAK plus 1. So the issue with this is that in the standard theory of projection valued measures, you're only supposed to integrate scalar functions. So this first integral is okay. G is a scalar function. This is fine. We know how to do this. But then the second integral, we don't know how to do. It's an operator valued function. We don't know how to integrate them against projection valued measures. And actually, that's the basically entire source of the difficulty for differentiating F tilde is making sense of the formula that's supposed to give you the case derivative. An object that makes rigorous sense of the object in quotations is called a multiple operator integral. And now you see why it's called a multiple operator integral. There are multiple integrals and operators. And this is still a hot topic in research. For the purposes of differentiating F tilde in the infinite dimensional case, the seminal work of Daletsky and Prime in the 50s, Bierman and Solomyak in the late 70s through 90s, and Peller in the early 2000s is most key, though a huge number of people have studied MOIs and their applications to perturbation theory. So here's a fake theorem, the real version of which is in an upcoming preprint. So I'm going to sketch for you a pseudo theorem that is too technical to set up in its entirety right now. So if F is just a tiny bit better than CK, then F tilde is continuously K times differentiable. And one can make sense of MOIs involving the case divided difference so that the case Fréchet derivative is actually this multiple operator integral. And, making sense of the MOIs is work that Peller did. The notion of tiny bit better than CK is one that I came up with, and it is vaguely locally approximable by polynomials in a certain norm that involves f bracket 1 up to f bracket k. The norm's a bit complicated, but it is basically a norm that tells you you are able to make sense of multiple operator integrals with f1 through fk here. And I'll just mention how close the space of functions for which this theorem holds is actually to CK. The work of Peller and my approach to this actually tells you that this, whatever this is, homogeneous Besov space, probably that's kind of a niche class of functions, but it contains the much more common Holder class, the CK functions whose kth derivative are epsilon Holder continuous, and all of these guys for all epsilon greater than 0 are contained in here. So you can be super close to CK, just a little bit better to make this theorem true, and there are counterexamples. So this is a proper subset of CK. I think that's about all I had to say for you guys today. Thank you very much for coming, and I'll take the questions.
Cool. Let's first thank the speaker in whatever format you would like to do so. All right, cool. So I'll start us off with the question. So on that last slide, is CK plus 1 included in a tiny bit better?
Very good question. Yeah. So CK plus 1 is better than CK enough.
Okay, cool.
It's better enough than enough.
Correct.
Any other questions for Vaki?
Right. Is this your 80 pages of work that we discussed at Bonner?
It's half of it.
So
So
damn.
this actually, so I told you this came up when I was considering free stochastic integration, and through a windy road, basically the space of functions that came out to be the one in this theorem was the correct one to consider for stochastic integration, but I also got this theorem out of it. The funny thing is that this theorem, since people mostly focus on unbounded operators, the approach is slightly different than this. And probably because most of the people who study this wanted to stick to unbounded operators, this approach just like never came to anyone's mind. But it's an approach that works precisely for the bounded operator case, and that recovers all of the previous functions for which this type of statement was known. So it's funny.
That's nice.
Other questions for Vaki?
Yeah, I have a slightly more elementary question.
Sure.
So when we were talking about functions from the spectrum to C or something like that,
Yeah.
why did we, it seemed like every time we had our spectrum in some sort of an ambient space and then we took the restriction, why not just consider functions from the ambient space? Was there a reason that we want it to be from the spectrum?
Yeah, so that was just to define f of a particular A. When you do the operator function itself, you do just take functions from the ambient space because you want to be able to apply this function to any A. So in principle, all you need is a function that's defined for, if you want to apply f to a single A, you only need it to be defined on the spectrum of A. But we wanted to consider everyone at the same time, and for that, we did consider just the whole ambient space as the domain. Does that make sense?
So it's not just notation. So in theory, if you had a function that's only defined on something that contains the spectrum of A, say, then you could use it for that A. So there's...
Yes, you could use it for that particular A, absolutely.
Okay.
Any other questions?
You sort of, when you went into the multiple operator integral slide, you said that the tough part was, just once you do the first integral, then you get operator valued stuff, and then you sort of like glossed over, like, oh, like Peller did this. Is there sort of like a general, like, hand wavy explanation, so that just like intuitively what he might have done that makes sense of it, or is it too hard to get into?
So here's the intuitive thing about what he did. So let's take the two integral case. What if your function g of lambda mu is expressible as g1 of lambda and g1 of lambda, g2 of mu? Then this double operator integral, you sort of intuitively know it should be integral g1 dp1 with b in between, and then g2 dp2. So somehow, if you have two variables separated, you should put the first variable on the left, and you should put the second variable on the right. And what he did is make define a class of functions where the idea is that you can separate the variables not in this simple way, but as an integral over a sigma finite measure space.
Oh, okay.
So it's these types of functions, and then the definition of this iterated integral is just put this integral on the outside and do this on the inside. Lots of details, but that's the idea.
Maybe I didn't understand one part where you were saying that he's like, consider these types of functions. Are these somehow dense, or like they're in whatever set of functions that you would want to consider, so that this is like, if you prove it for this, then it could be sort of extended, or is it just like a special case?
Which part are you talking about here?
You said that you want to represent functions in a suitable separable, like you can suitably separate them, and then you're able to talk about what like the operator valued integrals are.
Yeah.
But for any type of like maybe I forgot what G exactly was, but since it's like sort of defined on like sigma A1 on each of the spectrums, I was thinking like this like form that you said of where you circled like integral of sigma, yep, that whole thing. If I just gave you like a random G or something, is it sort of like can you approximate it with these, so that the sense that you make of this operator integral in this sense can be extended?
Yeah, so the usual way to prove that a given function lies in this class where you can separate it with an integral, it uses harmonic analysis. That's the main tool that the multiple operator integral people use to prove membership in their classes. It's not usually an approximation thing. It's like an identity that is obtained by doing harmonic analysis.
Oh, okay. Yeah, that makes sense. I thought you were going more like the functional analysis, or like the stuff from real analysis when you're trying to approximate things.
Yeah, sure.
All right. Cool, thanks.
So we're going to stop the questions now, because at the very least I need to go and I need to stop the recording.